Okay, let's get back to finishing this section. I thought I'd work through a couple of problems. Both of them are in your textbook, example 3-9 and example 3-10. And what they're going to do is incorporate this concept of a J number or the inertia that's associated with these rotating objects. And I think working through just a couple of these, and then you get some reinforcement with some homework problems and such, you'll be pretty familiar with those. So the first problem is example 3-9, showing us figure 3-10. And what this represents, it's a flywheel. And I'm going to go into some discussion about a flywheel and how they're used together with rotating electrical machines in another segment. But just for the time being, just know that a flywheel is something that can give us or it can possess great amounts of energy that we can use when we need it. And so, here's a flywheel in this particular situation. It's 1,400 kilograms. So, it's a heavy, massive thing here. It has a diameter of 1 meter, a thickness of 225 millimeters. And we can see that, it's showing that it's rotating. Now, when we have a problem like this, the first thing that we have to do is we have to determine what the J number is going to be. So for this particular problem, we've got these figures that represent different things. And so you really just basically match up the object that you're dealing with the derived J number. So figure 3-6 shows a solid disk of mass M and radius R. So that's what we have here. And so that's the J number that we're going to use to work this problem, okay? So the small m is the mass, the radius is the distance from the center to the outside of the flywheel, divided by 2, that gives us the J number. Now, what do we do with that? Well, what we're going to do with that is we're going to use that J number that we derive, and we're going to put it in our equation for kinetic energy. So, that equation looks like this. Okay, it's 5.48. We talked about this in an earlier video. And then here's the J number that we're going to derive, and then n squared. Okay, so back to this particular problem, and I'll just take this right over here. The mass of this is 1,400, and the radius, it says it's a diameter of 1 meter, so the radius is 0.5. That is squared. Of course, I want to square the 0.5 first, multiply it by 1,400, divide by 2. And as you can see in the textbook, we get 175. The units with that are kilogram meter squared. Okay, now we're going to take that. I'm going to slide this over here, and that'll give us the number that we need to place there for our J number for this particular problem. And so part A of this was find its moment of inertia, which we've done there. That's the 175 kilogram meter squared. Now we're going to plug that in here. I'm just going to drop the units because we know what those are. And then N for this is the speed. And the speed is in this equation is in RPMs. So we just get to plug it in there directly. That's a squared number. I'll go through the process. I'll multiply all this out. And when I do, and you plug this into your calculator, make sure it's working, I get 3.1 megajoules of energy contained in this flywheel. Now, I don't know if you remember this, and let me see if I've still got this in here. I want to show you a little something that's interesting, I think. Maybe I don't know where that is, but we worked an example earlier where we had a bus. Remember the bus? Yeah, here's the bus. All right, remember the bus, and it was loaded with 40 people, and we went through all that derivation, and we found out that the total energy in this bus that was moving down the highway was 3.25 megajoules of energy. Well, look at this. Here's this flywheel that's, you know, a meter tall and about a quarter meter thick. And that flywheel that weighs 1,400 kilograms possesses almost the same amount of energy as that moving bus. And like I said, later, I'm going to show you how we use or utilize a flywheel to impart a lot of energy quickly in certain applications. So let's take this one. Let me pause this, and then we'll get ready for the second example, 310. Our second example, example 310, it's different in that we're going to have to use two different J numbers to derive the total J value, or the total moment of inertia. So what we've got here is we've got this ring that he called an annular ring. And also we have this rectangular hub in the center of this thing. Okay. So, you know, we can picture what that might be. And again, this thing is rotating. And, you know, so it consists of two different shapes. So as we look that up, and I'll go back here just briefly, you know, what we've got is we've got this annular ring, and we also have a straight bar. And so we're going to bring both of those together to determine what the total J value is. So for the annular ring shape, this is the J number here, which is the mass times the radius 1 squared plus radius 2 squared divided by 2. And then for the hub, this part of our figure, for the hub, what we've got is this J number, which is the mass times the length squared divided by 12. Okay, so I'm going to slide this over, and I'm going to take for the ring, and I'm going to plug in what it's asking us here. What are the values for it? And again, the mass that's given is 80 kilograms. And these values were given in the figures as millimeters. So we know in terms of SI units that, for instance, 600 millimeters would be 0.6 meters, 800 would be 0.8 meters, and so forth. So we take the values that we need there to get that. Now, you know, for the annular ring, you know, we've got two measures, right? From the center to here and from the center to here. And so what we see is, you know, is the difference between those two. So that's where these values come from that he's taken away from that. Okay. So, you know, just make sure that you understand where those are coming from. And you know, just so we're clear here, I mean, I don't want to, you know, wear you out with the obvious, but, you know, this 800 millimeters is given as a diameter. And of course, the radius of that is 0.4. This 600 millimeter is given as a diameter. The radius of that is going to be half of that, or 0.3. And so that's where the 0.4 and the 0.3 come from in this particular equation. We plug in, we make sure we're careful with our calculator, get this taken care of. That's one of my 2's. It looks like an S. But anyway, I come up for the annular ring, has a moment of inertia of 10 kilogram meters squared. I go through the process for the rectangular hub, you know, this portion of our figure. And there's our equation for that. Mass of that is 20 kilograms. And again, we're given a length. How did we get that length? Well, you know, we go back to this measure and we just see that that is simply the diameter of the inner ring of the annular ring. And then this is 0.6 squared times 20 divided by 12, 0.6 kilogram meter squared. Now what we want to, if we're doing a total energy of this object, then we take this 10, bring it here, this 0.6 and bring it here, and the total J, or total moment of inertia, comes out to be 10.6 kilogram meters squared.